Good afternoon and welcome to H2REF's webinar, Exciting New Hydrogen Refueling Technology. My name is Stuart Anderson, I'm from Haskell and I'm the engineering manager here. We are responsible for design, manufacture and testing of the H2REF system.
Good afternoon, my name is Frederick Barth from H2Nova. I am the technical coordinator of the project and I'm very happy to present the results of this project in the name of the consortium.
Today's webinar is going to cover off a presentation, an animation, demonstration, and then we'll go through the results of the project.
And we will be answering questions. Please use the comments list below. And here we go. The H2REF project addresses the 2014 FCA GAU call topic on improving cost effectiveness and reliability of HRS. It started in September 2014. And ended after being extended at the end of last December. The industrial partners are Haskell, gas compression specialist and HRS manufacturer, Hexagon, pressure vessel manufacturing specialist, world leader in carbon composite vessels, CETIM, technical center for the mechanical industry, acting as coordinator of the project, and with supporting partners, H2Nova, originator and technical coordinator, bringing expertise on hydrogen technologies and design. The University of Technology of Compiègne, providing expertise on hydraulics. CCS Global, providing expertise on regulation codes and standards. And the consultancy Ludwig Boltko's Systemtechnik, specializing in energy and hydrogen, providing competences in techno-economic analysis.
The overall objective of the H2REF project is to develop a cost-effective and reliable hydrogen fueling solution. This is a graphical representation showing a simplified hydrogen refueling station. H2REF's primary focus is in the compression and buffering function shown here in the center of the screen. The purpose of the compression and buffer module, or CBM, is to take hydrogen from a depleting source, say 350 bar down to say 70 bar, and to put it into the vehicle in the most efficient way to give the highest state of charge. In our case, we're trying to achieve 5 kilograms of hydrogen at 875 bar. Traditionally, buffering of pressurized hydrogen is needed in order to be able to refuel the vehicle as quickly as possible, and refueling by direct compression would require a very large compressor. In conventional stations, compression and buffering are separate functions. However, for H2REF, we've developed a concept where those two functions are combined.
The H2REF concept uses hydraulic bladder accumulators to carry out both compression and buffering in what we call a compression and buffering module, that is a CBM. Hydraulic bladder accumulators are pressure vessels with a bladder. By injecting oil into the accumulator, you compress the hydrogen that is in the bladder and push it out downstream. The CBM has two stages. The first stage, medium pressure accumulator, takes hydrogen from the compressed hydrogen storage to fill the second stage accumulator using a 350 bar hydraulic pump. This is done multiple times until a pressure of 350 bar is reached in the second stage. An interstage heat exchanger allows to withdraw heat of compression. The second stage accumulator is actuated for dispensing hydrogen to a vehicle. While hydrogen is allowed to flow into the car tank, oil is injected using a high pressure pump to reach the required pressure at the end of fill, which can be up to 875 bar. Pre-cooling and dispensing flow control continues to be required just as in any HRS. So what we have is a novel combination of mature and scalable technologies for hydrogen dispensing, that is, hydraulics and pressure vessels.
We're now going to talk about the bladder accumulator design. The compression process is based upon hydro-pneumatic accumulators, which is a more reliable economic solution with higher performance. Bladder accumulators are nothing new and are commonly used in hydraulic systems for energy storage. However, the H2REF process uses them slightly differently. H2REF is using a novel approach of using them to compress the gas. We're also using them in different operating conditions. We're using them for hydrogen versus nitrogen at much higher pressures, almost 4.5 times greater than conventional bladder accumulators, will also got a much greater volume. The result is the creation of a carbon fibre composite shell with a plastic liner, which allowed us to dictate the size of the accumulator required for our process. If you look at the bladder accumulator to the right hand side, the process is as follows. Gas enters into the bladder, is forced out against the shell of the composite. It then comes down to where the hydraulic fluid enters onto a poppet valve. This poppet valve performs two functions. Firstly, to close the hydraulic port when the bladder is fully expanded, and secondly, to prevent the bladder from being extruded when the hydraulic oil is released.
So what are the main advantages of the H2REF concept? Well, first of all, it implements serially produced components from mature industries, which are hydraulics and pressure vessels. This helps to decrease the capex while providing excellent durability and reliability. Also, we have a scalable solution thanks to the combined high scalability of hydraulics and carbon composite pressure vessels. It's flexible thanks to the wide operating pressure range of its components. It provides reduced energy consumption thanks to taking advantage of the varying pressure upstream. That is, all upstream pressure that is available is used and is not lost, as may happen in conventional compressors. Also, it can be a low noise solution because the hydraulic power unit is housed in a separate enclosure where you don't have any hydrogen, so it doesn't require high ventilation and can be easily insulated.
We'll now go through a brief H2REF animation showing how the H2REF process works. This shows a representative fueling station. The hydrogen vehicle pulls up to the dispensing point. The nozzle is then connected up to the car. We'll now walk through the process to understand how the H2REF system gets the hydrogen to this point. There are several key modules in the H2REF system. There's the hydrogen line to the dispenser, the gas supply, the compression buffer module, the process chiller, and the hydraulic power unit. In the hydraulic skid, there's a hydraulic tank, including motor and pump set, air compressor, PLC, and obviously the hydraulic intensifier. In the compression buffer module, there's the 4 quads, gas process heat exchanger, and all associated valves and fittings. Here you've got the hydraulic oil going into quad 1, feeding the gas into quads 3 and 4, then quad 2 into 3 and 4. This process continues up until quad 3 and 4 are up to 350 bar. On the left hand side the gas comes in, goes into quad 1, hydraulic comes in the bottom, squeezes the bladder accumulator, and the gas then goes into quad 3 and 4. Once we're up to 350 bar, in quad 4, then the hydraulic intensifier. We'll bring in the hydraulic oil and squeeze the bladder to produce gas pressure up to 900 bar. That goes out the dispense line, through the heat exchanger, and along to the dispenser. Bank 3 or quad 3 is then used to replenish quad 4 so that we're ready to do back-to-back refueling. Process then starts again with quad 1 and quad 2, replenishing gas in quad 3 up to 350 bar. This will take approximately 5 cycles. We'll now have a look at one of the bladder accumulators in detail. So here's a single bladder accumulator. There's the hydraulic poppet valve. Gas comes in the top, expands the bladder, and the bladder then depresses the poppet valve at the bottom. Each quad is made up of 4 bladder accumulators, and there are 4 quads in the system. 3 medium pressure, 1 high pressure. Now show the whole process in operation. Gas comes in, quad 1 feeds, quad 2 feeds into 3 and 4. And then once quad 4 is up to 350 bar, then the hydraulic oil from the hydraulic intensifier squeezes the bladder accumulators, which pressurises the gas in the dispense line through the heat exchanger up to 900 bar and out to the vehicle. As you can see, the footprint is very efficient, and this system can be used on any vehicle type. I hope that's been useful in giving you an understanding of how the H2REF process works.
In developing hydrogen accumulator-based compression, we were faced with 3 challenges. The first one was to develop a 900 bar accumulator in carbon fiber composite. The second one was to identify a bladder resisting to hydrogen pressure variations. And the third one, which was wider, was to develop the process and test it. So let's look at these challenges in more detail. First one, accumulator qualified for service at 900 bar. An accumulator in composite is built like a composite pressure vessel. It has a shell in carbon composite fiber. It has a liner in polymer. It has metal bosses where you have the gas exit on one side and the hydraulic port on the other side. And it has a bladder in the elastomer. Now, while this looks very much like a composite pressure vessel, the main difficulty is that you have a much larger opening than what you have on normal pressure vessels. And this large opening is required to allow the replacement of the bladder. And that creates a specific challenge in terms of structural design to withstand the 900 bar operating conditions. Also, you need metals that are compatible for hydrogen service. This is due to the fact that some hydrogen permeates into the oil, so those parts are not completely free of being exposed from hydrogen. So after design of the accumulator, there was a second sub-challenge, which was design qualification. The problem is that there are no standards for carbon composite accumulators, so qualification criteria for use of the accumulator in the CBM prototype had to be agreed within the consortium on an ad hoc basis. So 2 qualification criteria were applied. The first one was to demonstrate a minimum burst pressure of 2.25 times the maximum allowable pressure, that is 2025 bars. And it turns out that 4 design iterations were required to achieve this target. So in this process, 2 designs were adopted: a medium pressure accumulator designed for service up to 500 bar maximum, and a high pressure accumulator for service up to 900 bar. The second criteria was achieving a certain cycle life. The medium pressure accumulator was cycled to 500 bar, not 1050 as shown here on the slide. It's 500 bar for the medium pressure accumulator up to 80,000 cycles. And the high pressure accumulator was actually cycled twice to 40,000 cycles to demonstrate repeatability. It was judged that it was preferable to test two accumulators to 40,000 cycles rather than just one to 80,000 cycles. In parallel, there was interaction with the SEN Technical Committee 54, which oversees standardization in Europe for all pressure vessels, in order to get coverage by SEN standards of accumulators made of carbon composite material. And actually, we were successful in having them agree to proceed to a change of scope of this technical committee to address accumulators in carbon composite. Let's now move to the second challenge, which was to find a bladder material resisting to hydrogen pressure variations. The problem is that elastomer materials exposed to pressurized hydrogen tend to blister due to hydrogen permeating into the material. And this blistering occurs when the pressure is reduced. And you have very large pressure variations in the CBM system, up to 600 bars of pressure decrease in the second stage of the system. So first we looked into the phenomena in order to determine how it can be mitigated through the right operating conditions. And then we tested the various materials using a unique testing facility that Hexagon has on its site. And as far as we know, it's the first time that this type of testing is performed on elastomers. Over 20 tests were performed, and a material offering good compromise with regards to resistance and manufacturability was selected. In the middle, you have a recording of a test done on one sample with pressures varying from 700 bar to 150 bar. The cycle consists in varying the pressure up to 700 bar, holding pressure for 15 minutes, and then decreasing at a rate of 350 bar per minute down to the minimum pressure. On the right, you have examples of results. So on the top, it's a negative results where you have blisters that appear inside the material that would lead to its rapid deterioration in a system. And on the bottom, a material without any blistering, therefore a suitable material for the application.
Okay, we're now going to talk about challenge number 3, which is to do with the process development and testing. In order to develop the concept, we've had to utilize a number of different test facilities to conduct different tests and parameters to do with the functional testing and also the endurance testing of the system. On the left-hand side, we've got a test bench which shows the folding behaviour of the bladder accumulator. This was conducted by UTC, and they did it to show that when the hydraulic oil was injected, how the bladder would fold, and also as the gas was removed. In the centre, this is a hydrogen test facility in Sunderland. This allowed us to conduct full-scale CBM testing in a closed-loop configuration with both nitrogen and hydrogen. On the right-hand side, this shows the bladder accumulator endurance testing done at SATEM, which allowed us to accelerate the endurance testing on these bladder accumulators. As mentioned above, the functional testing was a key part in the process to build confidence the system was going to operate the way we wanted it to operate. For the functional testing, we chose to take a sequential approach, utilising a single system setup. The sequential approach was needed as we didn't want to test both new processes and components at the same time. This also brought about some key advantages. We were able to utilise a full-scale system, not just a test bench. We had reduced the overall cost for the system by utilising the same equipment, but just building on it. We built confidence in the system process without the need to start from scratch every time. And we built up the functional and complexity of the system using a known baseline. The main phases for the system development were: we initially started with a test bench and a known product, so a piston accumulator, to prove the functionality of the system, testing the injection and release of the oil under a controlled condition. We then progressed to the single bladder accumulators for medium pressure and high pressure using the same configuration as the piston accumulator. This then allowed us to get more confidence and move to the full system testing with the 4 quads, 3 medium and 1 high pressure, and progressed to full system CBM. Some of the new functions which we had to validate included the accurate control of the amount of hydraulic fluid injected and released from the bladder under a controlled fashion, handling of any hydrogen migrating into the hydraulic fluid, detecting of the bladder failure and actions to prevent overpressure of the oil tank and contamination entering the gas system. One of the unique factors of the H2REF project was our ability to test a full-size system in both nitrogen and hydrogen. In front of you can see the aerial shot of the hydrogen test facility in Sunderland. On the left-hand side here, in the ATEX zone, is the H2 and N2 source gas in cylinder bundles. Beside that is the hexagon vessels for the gas recirculation and storage module. In the middle, also in ATEX zone, is the gas skid or compression and buffer module. In here, we had the bladder accumulator quads, 3 medium pressure, 1 high pressure, the gas process pipework and heat exchangers, and at the back we had the oil and gas separator for where there was a bladder failure or bladder issue. This also fed into the gas analyzer, which is in the non-ATEX zone, to see if there was any hydrocarbons or impurities in the gas. On the right hand side, you've got the hydraulic skid, and in there you had the hydraulic power unit, including the hydraulic intensifier, the PLC and fire safety system. Outside you had the air blast chiller for cooling the hydraulic skid, and we also had a process chiller for cooling the gas skid. An oxymat and calomat system were also included in here for monitoring the gas in the nitrogen blanket and replenishing it if required.
Now let's move on to the results. This slide shows the results of the functional testing of the medium pressure accumulator using the system in test bench configuration. It's a configuration where the accumulators are tested individually. The objective of this test is to check that the accumulator behaves as expected. This concerns not only the bladder, but also the hydraulic port with the poppet valve, which needs to open when oil is injected, needs to stay open when oil is released, and needs to be closed by the bladder pushing on it as it expands. So in this test, a volumetric ratio of 90% was applied, meaning that the amount of oil injected is equal to 90% of the volume of the bladder when it's fully expanded. That leaves 10% when the oil is injected. The test was done against the back pressure of 30 MPa, 300 bar, and there was a 60-second hold time at high pressure. That is when the bladder is fully compressed. In the chart, you see on the top chart, you see the black curve, which is the volume of oil injected up to 60 liter with a 60-second hold and then a controlled release. The little step that you see there is an anomaly that was corrected afterwards, a problem in the sequence of valve opening. In blue, you have the pressure inside the accumulator going up to 35 MPa, then slightly decreasing during the hold because the temperature decreases a bit during the hold, and then the drop of pressure following the release of oil. In red, you have the temperature inside the accumulator. It's measured actually at the outlet of the accumulator, so it's only reliable when gas is being flowing out of the accumulator. You see that the temperature increases to 140 degrees when hydrogen is being pressed out, which occurs when the pressure inside the accumulator exceeds 30 MPa, since we have a back pressure regulator that maintains 30 MPa in the accumulator. Now, this temperature of 140 degrees in the beginning, it's read on the right chart, up to 170 degrees is higher than expected, and it's due to heat accumulation in the piping and test bench configuration. Still, the bladder did resist to these higher than expected temperature levels. Normal maximum temperature expected was 120 degrees. So it shows good resistance of the bladder to deviations from the expected temperature conditions. On the bottom chart, you see a recording of the hydrogen concentration in the oil tank. So as hydrogen permeates into the oil, it is returned in small quantities into the oil tank. And this recording shows that the amount of oil that is released into the oil is quite small, only about 0.2 liters of hydrogen at atmospheric pressure per actuation. So this is fully a manageable permeation. Next are results regarding the operation of the first stage of the complete CBM system. In this test, the system takes hydrogen from a source initially at 10 MPa or 100 bar and brings it up to 30 MPa. The top chart shows the amount of oil injected and released in each accumulator bank. That's 200 liters. The bottom chart shows the corresponding change of pressure in blue and the change of temperature in the accumulator. That's read on the right scale. And in green, the increasing pressure in the downstream tank up to 30 MPa. You can see that the pressure increases in the downstream tank when the pressure in the accumulator in blue exceeds the pressure in the downstream tank. One point to note is that there is a very big pressure drop in the system. This is shown here by the difference between the pressure in the accumulator and the pressure in the downstream tank, which reaches 150 bars at the end of compression. Another noteworthy point is that when you process the data, you find that the applied hydraulic power is 27 kilowatts, whereas the actual power of the hydrogen power unit is 70 kilowatts. And this difference is due to a lack of tuning of the hydraulic pump. Nonetheless, the process works as expected, but capacity can be strongly increased. Actually, we estimate that it could be tripled by system optimization, addressing the pressure drop and improving the setting of the hydraulic pump to get the 70 kilowatts of nominal capacity. This slide shows results regarding the operation of the second compression stage used during dispensing. It was performed with the CBM in the so-called junior CBM configuration with only one accumulator per bank instead of 4, and operating in manual mode due to a problem we had at the time with the control valve in the second stage. The recording shows compression from 30 to 90 MPa, that's 900 bar, and dispensing against the back pressure of 80 MPa. You see in the chart the black curve showing the amount of oil injected, increasing to 50 liters. The blue curve showing the pressure in the accumulator, increasing to 90 MPa and then stabilizing at 80 MPa thanks to the back pressure regulator. The green curve shows the pressure in the downstream tank, which increases when a valve is opened, and the back pressure regulator maintains 80 megapascal in the accumulator, allowing some gas to go into the downstream tank. And you also have the gas temperature in red, which increases to 110 degrees Celsius, which is the expected temperature for this operation. Below, you see a chart showing the hydrogen concentration in the oil tank. So showing the amount of hydrogen permeating into the oil and released into the oil tank. This quantity is quite small, as the concentration only increases by 0.2% in the tank for this dispensing operation. So to conclude, the process works as expected, but further testing is required for measuring performance of the complete system.
One of the final tests we conducted in this project was a contamination test. For this test, we had to create a separate test rig, which was assembled to take 2 bladder accumulators. We had hydrogen from a known source feeding into the 2 bladder accumulators. The 2 bladder accumulators cycled with each other, and then we could take any samples that we liked. The purpose of this test was to review the potential contamination of the gas when the bladder accumulators was subject to a rapid cycle and hold test. A total of 4 samples were taken, and the H2 cleanliness levels were checked against ISO standard 14687, standard required for fuel cell vehicles. The initial sample was taken from the H2 bundle from the source, so we knew the baseline of hydrogen we were getting. We then filled the accumulators to 70 bar and injected and released oil 5 times to increase the pressure to 250 bar. The second sample was then taken at this point. We then continued to inject the oil 20 more times to 250 bar with a hold of 10 minutes. A third sample was taken after this exercise. We then injected oil to 300 bar and held it overnight. We then released the oil and took a further 4th sample. All these samples have been sent for analysis.
Now let's go to the results of the techno-economic study that was performed. So the objective of the study is to compare the cost and power consumption of the CBM concept with a benchmark HRS, and the assumptions for the benchmark HRS are covered here in this slide. We're speaking of a 400 kilogram per day capacity HRS, assuming a constant load of 30 kilograms per hour during 12 hours per day. It's a 2-stage system, with the first stage taking hydrogen from a mobile storage system, a trailer, which here in this case is assumed to be a high pressure trailer, a depleting storage, and that first stage with a power compression capacity of 20 kilograms per hour, filling a medium pressure buffer at up to 50 MPa, and the capacity of that buffer is 120 kilograms effective storage. The second stage is a high pressure compressor, taking the hydrogen from 40 to 95 MPa with a compression capacity of 50 kilograms per hour, and accumulating that hydrogen into a high pressure buffer where the pressure is between 85 and 95 MPa. Now, these figures were obtained by determining the optimal distribution of compression and storage capacity for this architecture. It is also assumed that this benchmark station is operated in an optimal way, that is, taking hydrogen straight from the trailer as far as possible, and then cascading using hydrogen from the storage buffers, first the medium pressure buffer and then the high pressure buffer. And the figures, the percentage figures in red, show the share of a load which come from the different parts. So you have 30% coming from the trailer, another 20% coming from the medium pressure storage, and the remaining 50% coming from the high pressure storage.
So here you have the comparison of the investment cost of a CBM HRS with the benchmark HRS. The CBM cost projection considers process simplification as well as small series production of 50 units per year. On the left, you have the cost projection for the state-of-the-art HRS, which is the benchmark HRS. The total cost of the hydrogen refueling station is 1,350,000 euros, 727,000 euros of which are for functions related to compression and storage. On the right, the CBM-based HRS for the same capacity, assuming 50 units per year. Total cost of below €1 million, with the CBM part concerning compression and buffering of 436,000 euros. So you have a projected cost for the optimized CBM solution that is 40% below benchmark cost for the same functions. And that results in an HRS cost overall 28% below benchmark.
Here is a comparison of the power consumption of the CBM HRS with the benchmark HRS. This is based on simulations, and for the CBM system, an optimized solution is considered, where all the pressure drops have been minimized and where full use is made of the available hydraulic power. The chart shows the average power consumptions for the different types of HRS, starting completely on the left with the case of the benchmark HRS, but without optimized use of the available pressure. That is that all the hydrogen in the trailer is compressed rather than some of it being used directly to dispense the vehicle. And there you have a power consumption of 4 kilowatt hours per kilogram. In the trailer utilization case, this is the optimized benchmark HRS, where the available pressure in the trailer is utilized, and there the average electricity consumption is 2.4 kilowatt hours per kilogram. So we're speaking of average electricity consumption because that power consumption depends on the pressure level in the trailer. For the CBM HRS, which also makes best use of the available pressure of the trailer, the power consumption is reduced to 1.05 kilowatt hours per kilogram. And to that, you need to add the power consumption for the pre-cooling, but which is the same for all the cases. So overall, the power consumption of the optimized CBM solution is projected to be 56% below the benchmark case, and that results in an HRS power consumption of 37% below benchmark when you include the energy needed for pre-cooling.
One of the main considerations for any hydrogen refueling station is going to be the ongoing OPEX and maintenance costs. And with our system, it's no exception. One of the key maintenance tasks is going to be around the bladder replacement. However, the way we've addressed this is by designing an easily transportable quad frame, quad being 4 bladder accumulators per frame, which can be easily installed and removed by a forklift truck due to the easy centralized connection point for the hydraulics, single manifold block at the base, and a simple common gas inlet line at the top. The approach we've taken is that if a bladder needs replaced, a full quad will be removed. This will reduce the amount of downtime and it also means you can take the quad to a clean environment to be inspected and conduct the bladder replacement. Current projections show that the bladder should have a cycle life in excess of 100,000 cycles, which means, depending on the station utilisation, would be around about 3 to 5 years. Therefore, we're not expecting this activity to be taken on a regular basis. The graph to the bottom here shows the projected maintenance cost based on a 200 kilogram a day station with an average 80% utilisation, with a single cycle profile of 2.5 cycles for quad 1 and quad 2, and 1 cycle for quad 3 and quad 4. This is based on a 5 kilogram refuel. As you'll see, the annual cost of the bladder replacement could reach less than €1,000 per year, with further optimisation of the bladder durability. As part of the ongoing H2REF dissemination activities, we've recently conducted a demonstration event at the Haskell Hydrogen Facility in Sunderland. Here's a brief overview of the H2REF demonstration event that took place a few weeks ago. We went through the full H2REF project, showed them around the system, and concluded with a physical demonstration showing the dispensing activities. The full demonstration event is available on our website.
An overall conclusion that can be drawn from the results of the project is that accumulator-based hydrogen compression for vehicle dispensing has been validated at full scale in a relevant environment. That's TRL 5. Another result we would like to highlight relates to standards development. H2REF has worked with CEN TC54 to facilitate EU-wide market acceptance of accumulators with a composite enclosure. And CEN has actually agreed to proceed with changing the scope of their TC to include composite accumulators, and they are presently developing a plan on how to proceed. This will definitely facilitate EU-wide market acceptance of the H2REF CBM solution. So next steps are to bring accumulator-based compression to TRL 7. This means further optimization, for instance, by minimizing pressure drops and making full use of the available hydraulic power. It's also process simplification, eliminating all unnecessary components to minimize cost. It's further functional and endurance testing, and overall, it's demonstration of the process in a commercially operated fueling station. Another step is to support the further development of the required RCS framework, that is the CEN standard. And finally, we would like to develop and demonstrate accumulator-based compression for high-capacity dispensing, up to 2 tons per day, taking advantage of the scalability of this solution.
Okay, thank you for listening to the presentation today. What we'll do now is we'll look into a couple of the questions that you've been putting in. Okay, first question here then. What's the expected cycle life of the bladder accumulator? Okay, probably the best way to break this one down.
To distinguish the shell and the bladder.
Yeah.
Yep.
Okay, that's good. All right, so the shell side of things, base assumption around the shell, 15-year life, 20 cycles per day, 2.5 cycles each refueling. Is that
Yeah, right. For the
basis
medium,
one?
that's for the medium pressure stage.
Medium pressure, good one. Yeah. So there's medium pressure and high pressure. Medium pressure, expected life for that is.
So if you multiply 20 fuelings per day times 2.5 times 365, by memory, that's over 15 years. That's the target. That's about 275,000 cycles.
Yeah. Okay, I'll take your word for it. 275,000 cycles. Demonstration, we've probably achieved over about 80,000 cycles.
For the medium pressure, we've demonstrated 80,000 cycles. Carbon composite fibers have the capability to a very long cycle life. So we expect to have the capability of 275,000 cycles. But it's a matter of demonstrating that. Also following standards which today are not developed for this application, accumulators and composite material. That's why we, as we indicated in our presentation, we have interacted with the standards arena to have work started on standardizing the testing requirements for composite pressure vessels. And the idea is to have that ready when we are ready to commercialize this solution.
Working closely with them, aren't we? So that's so the shell, medium pressure, high pressure shell, bladder itself.
So for the bladder, we're not targeting a lifetime 15 years, but rather it's considered to be a replaceable part that would have a lifetime of 2 years. Actually, what determines the lifetime of the bladder is the extent to which it is folded. That's resulting from the volumetric ratio that we apply. And we apply a pretty high volumetric ratio to maximize compression effectiveness. So in our testing, we did not get the 35,000 cycles, but we know why. Our design is not fully optimized yet. We know the solution, and we expect to that this will fix the situation of excessive folding that we had in our prototype. So that will we expect that we'll be able to show the expected cycle life in the next iteration.
Yeah, that's true. It's worth noting that the bladder's the same for medium pressure and high pressure. So
good point. Yeah, so it's the same bladder for the high pressure and the medium pressure accumulators, and it's the medium pressure stage which is the most demanding. That's where you have the most cycles and where you want to have where you want to have a very good volumetric ratio.
Exactly. Good. Okay, well, hopefully that's answered that question. Let's see what else we've got here. Okay, here's a good one. What happens if there's a bladder failure?
Mm-hmm. Yeah, indeed. I mean, that is
definitely an issue that could.
Because the bladder is the weak element in the system, and that's something that we have, of course, anticipated. So an important thing to note, though, is that if you do have a tear in the bladder, since you have balanced pressure on both sides of the bladder, you do not have oil gushing into the gas side. You rather have gas diffusing into the oil, and that has immediate effects on the hydraulic side. It results in more volume of oil being released than injected, and also pressure increase in the return line. So we have multiple ways to detect this situation and stop the system as soon as it begins to happen. It's quite sensitive, and therefore we have a solution that reliably prevents continued operation with a torn bladder, and this is what really prevents oil from getting into the gas circuit. So when you detect a bladder failure, what's important is to stop operation and replace the bladder. And we've actually really thought about an integration solution that allows to do that effectively. Maybe I should let you talk about that.
Yeah. So as
you thought that.
Yeah, as we've indicated before, the system's a modular structure. So we have these quads. So the quads are in four bladder accumulators in a quad. And you replace a full quad because at this stage there's no indication to which one of those bladders has failed. So we take out the full quad, we replace the full quad with a new one, and it allows us to off-site review any issues and identify any problems from that point. So we can isolate the gas side, isolate the hydraulic side, and remove the quad itself.
Yeah, right.
Anything else to cover on that?
Right, so that way the bladder replacement is really done in controlled conditions in the shop, and you get the operations done in the field are really basic exchange of equipment. So that's done in a safe and reliable way.
Okay, good. Let's see what other questions we've got here today. Okay, when do you see this technology being commercialized? Right, well, this is a good question. R&D project, this is the first time we've implemented anything of this sort of project. We've addressed, in the 3 years that we've been running the project, we've addressed the main technical issues. We think we've addressed the main technical issues.
Yeah. And done that at full scale, which is
exactly, it's not yet
scale 1 prototype.
So we think we're hovering around the TRL5, we're validating it in a relevant environment being the test, the site that we've got available to us here.
Right, yeah, we're a bit short of them actually demonstrating it. That would require more operating time. But definitely
that'll be the next phase, next step in the process. So yeah, to answer the question, I suppose we need to optimise the solutions. We need to have a look at more maybe cost drive on some of it, making it a little bit simpler. Have a look around the design optimization.
Yeah, definitely. We have a complicated system now. As we explained, we have a setup which was intended to do different things that went through different phases. So we have a lot of elements in there that are not needed in the device that would simply compress hydrogen in the fueling station.
Yeah, the final design. Yeah. So I suppose next phase we'd be moving it from the TRL5, so the technical validation, into the actual demonstrating in operational environments. TRL7.
Yeah, that's right.
That's what we're aiming for.
Yeah.
Ideally, probably what, 3 to 5 years off, is it?
Yeah, it could be. I imagine that it could be in 3 years that we have reached TRL7, and therefore a product which is really ready to be implemented in commercial operation.
Excellent. Okay, perfect. Unfortunately, I think we're running out of time here, so I don't think we're going to be able to answer any more questions today. What we should be able to do, though, is publicise all these questions, get back to people directly. I still see there's a couple more questions here that we need to answer. And then we'll publicise that on our website along with the webinar that we're doing just now, so that will be on the website as well, so you can get access to that. So the last thing to do is to say thank you very much for your participation today, for listening into this, and feel free to contact myself or Fred or any of the consortium members if there's anything that you've seen today that's what you've got some interest in.
Yes, indeed. Yeah, we hope you found the presentation interesting and this technology promising, and we look forward to hearing from you.